Don't judge me. We're going to start with hopefully a question that we can answer, because it is review. Review. So, first question, how do we add fractions? I want to add 1/4 and 2/5. Very good. Same denominator. We need to rewrite the fractions with a common denominator. I need the bottoms to match, and then I just add the tops. Yeah? We're going to do an example, because it's probably been a while since we've done this with algebra. I have two fractions, 3 over x, 2 over x minus 1. I want to add the fractions. And the idea is pretty similar to how I would squish 4 and 5 together. The common denominator for 4 and 5 is 20. I'd multiply the 4 fraction by 5 top and bottom. I'd multiply the 5 fraction by 4 top and bottom. Same idea with algebra. I'm going to multiply the first fraction, top and bottom, by the second denominator. X minus 1, x minus 1. I'm going to multiply the second fraction, top and bottom, by the first denominator. And we do that because now I can see both fractions on the bottom have x times x minus 1. They may have them in different orders, but for multiplication, we know that order doesn't matter. They are commutative. The question is, what am I left with in the numerator? And I see a 3 times an x minus 1 plus a 2 times an x. And I want to make that as pretty as possible. What should I do to get rid of those parentheses? Distribute. Very good. Nice use of math vocab. 3 goes through this parentheses, x goes through that parentheses. So 3x minus 3 plus 2x over x squared minus x. I see one more thing that I can do. Who else sees it? In the top, there are two terms with x's in them. So 3x plus 2x is 5x. Yeah. Perfect. Happy face. Not fun by any means, but something we've done before. Vaguely familiar, tickle on that spot in the back of our brain. What we are doing today is the reverse of this process. And the reverse of this process is called partial fraction decomposition. It's the little things that make me happy. Partial fraction decomposition. I am taking one big fraction and splitting it up into a bunch of small pieces. That's what decomposition means. It takes a big thing, breaks it down into its pieces. We're doing that with fractions, thus fraction decomposition. Yeah? We don't want to have to write that every time we want to do it. That's a lot of words. I'm going to call these PFDs, partial fraction decompositions. Find the PFD. I'm sorry to my AP Stats student because I know that sounds like a PDF, but no, probability distributions are a whole different thing. The PFDs in pre-cal. The question is, how do I find PFDs? So we're going to go through the step list first, and then we're going to do nothing but examples for the rest of the class. Really? Yes, really. I don't know, however long we need. We'll keep going until either you're crying or you feel comfortable with what we're doing, one or the other. It's an elective. Just remember, you chose this. You chose this. All right. How to find a PFD, how to find a partial fraction decomposition for a rational expression. I know, I'm in stats. I want to say PDF too, but it's a PFD. Oh yeah, that too, yeah. So first step, I want to split up the fraction. I should start by splitting up the denominator, because if I scroll back up, I can see from here going backwards, I at some point end up with a factored denominator, which then gets separated out. Because I can see these two factors here are in separate fractions when I started. So that's what we're going to do. We're going to undo this distribution process and factor that denominator to get it into factors, and then split those factors up into separate fractions. So very first step, factor the denominator. You need to do it fully. All the factors, all the way down to a bunch of binomials or unfactorable quadratics. I shouldn't have anything higher than a second power. And we have a couple of tools in our toolbox for doing this. The first thing you should check anytime you're asked to factor is, are there common factors? Do they all have an x in them? Pull an x out in front. Are they all even? They're divisible by 2. Pull a 2 out in front. Look for something that every single term has in it. The next strategy, if it is quadratic, an x squared, and its leading term is 1, I can play the x game. If the polynomial has 4 terms, or it is a quadratic and the leading term is bigger than 1, I can factor by grouping. None of the questions that I ask you are going to go beyond those 3 methods. All of them can be solved that way. If, when you take big fancy math in college, you encounter something bigger than a quartic, bigger than a power of 4, remember that we know how polynomials behave. We can find rational zeros using the rational zero theorem. I know what the rational zeros look like, the ratios of the first constant to the last constant. I know how to use synthetic division to divide them out to make the polynomial smaller until I know how to factor it. I won't ask you to do that here. We're only going to be using these tools. Okay, so the next step. Now that I've got the factors of the bottom, I want to split my fraction up. And I'm making room because there are 4 possible things that you might see. So deep breath. We have 4 possible cases when we get to step 2. The first is that I have, whoops, that's not what I meant to do. I have linear factors and I have no repeats. So that would look like in the bottom ax plus b times cx plus d. They're binomials, they're fully factored, they're linear, but they're different. The constants in them are different. No repeats. So I'd say linear, meaning it's linear functions, and there are no repeats in the functions.
Oh, meaning linear squared.
Comma, no repeats. Yes, linear terms, no repeats. Sorry, linear factors, no repeats. In the numerator, it's a function of x. I don't really care what the numerator looks like right now. I'm focused on the denominator. I want to split the bottom up. If the factors in the bottom are linear, when I split up into separate fractions, the numerators will be constants. And I'm going to scroll back up to our example in just a minute once I see pencils stop moving. We started these notes by adding fractions. If I go back up, look at what was in the top of those fractions. Constants, 3 and 2, right? Yeah, same thing we're looking at here. When I split them up, I want to split it up so it's numbers. I won't know what they are. You are literally going to write what I have there, A, B. We'll figure out what those numbers should be later. Okay, next one is linear, but I do have repeats. Ax plus b squared, or cubed, or to the 4th, or to the 100th. I don't care. Yes, we are repeating that factor some number of times. I'm using 2 for an example, but it doesn't have to be 2. Any guess how many fractions I'm going to need when I split this up? 2, because I've got 2 factors in the bottom. Yeah, that makes sense. I want as many fractions as I have factors. I know those factors are linear, so I know I'm going to shove constants in the numerators. The question is what goes in the bottom. And this is where it gets a little weird. The first fraction is just one of the factors. Sensible. Second fraction is where it gets a little funny. Second fraction is ax plus b squared. When you have repeated factors, you start with one copy of the factor, and then each successive fraction gets another copy until you reach that power. So if this were to the third, I'd have an ax plus b, an ax plus b squared, and an ax plus b cubed. Yeah? If it was to the fourth, I'd have to go all the way out to ax plus b to the fourth. So whatever the power is here, that's the number of repeats I need. The exponent goes up by 1 every fraction until I reach the power I need. Yeah? Okay, so the other option when we factor is I end up with quadratics that I couldn't factor playing the X game or by grouping. They just aren't factorable because they sit way up above the axis and they don't have real intercepts. They had imaginary intercepts. They're going to follow a similar pattern. So I can have quadratics that don't have repeats. Or I can have quadratics with repeats. Been listening to that all day. The ceramic class above us getting violent with their clay. A little bit. All right, so first question is, what does this look like? And it's going to look very similar to how we started with the others. Quadratics have an x squared term in them. So instead of ax plus b, I have ax squared plus bx plus c. And for the no repeats, I'm going to have a similar pattern, but it's going to have different constants in front. dx squared plus ex plus f. Different quadratics that are not factorable, cannot factor. How many fractions do I need? How many factors do I have? 2, yeah. Each factor in the denominator gets its own fraction. So ax squared plus bx plus c, dx squared plus ex plus f. The numerator is going to be 1 power less than the denominator. When we had a linear factor, we had a constant on top. Now I have an x squared on bottom. What am I going to have on top? 1 power less would be what? X, a linear function, yeah. Oops. Last one, yeah. Quadratics with repeats, meaning I have a quadratic in the bottom times itself however many times. And this is a combination of 2 patterns. Let's see if we remember. How many fractions am I going to need? Show me on your fingers. 2. because I've got two factors, right? It's squared, two fractions. The question is, what goes in the bottom? And this follows the same pattern as the linear with repeats. I copy the factor to the first power. The next fraction is to the second power. Quadratics with repeats behave similar to linear with repeats. What goes in the numerator? One power less than the denominator. The x, good. Ax plus b, cx plus d. You'll notice I'm using capital letters in the numerator to help keep track of those constants and keep them separate from the bottom. So we usually use capital letters in the top of our PFD process. We have a whole bunch of fractions that are separated. And I know what the bottom is. These should be numbers down here with x's. The question is, how do I figure out what goes on top? And that's where some algebra comes in. The next step in this process, the goal is to get rid of the fractions. I don't want any fractions in my expression. And I know to get rid of fractions, I multiply by the denominator. So if the number on bottom, same number on top, those things cancel. Yeah? So I am going to multiply. Focus, children. Multiply the whole equation by the original denominator. Everything by the original factor denominator, yeah. No, this is the how-to, and you distracted me. I forgot what I was writing. We haven't done any examples yet. I'm just telling you how to do it, so you've got the step list. That was the cases for step 2. It's only going to be one of those usually. Cases for step 2. Once I have multiplied by that original factor denominator, I shouldn't have any fractions anywhere. And the next step is just to simplify and solve for those missing constants. When you do this on your homework as independent practice, you are going to get this step list out and slap it on the table next to your Chromebook. Yeah? You're going to follow the step list, and you're going to have examples after this step list to provide you with a visual for what it looks like in practice. Do not ask me questions on how to do your homework unless you have your notes with you. Use the resources you have, yes? So get your notes out, try it, and then if you get stuck, I will help. But you should all have been writing this down. We all have it now, yeah? Everybody was here today. Okay, so all we're doing for the rest of today, examples. Practice, 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 yeah? We're going to start with the most basic. We're going to go back to that first example and see if we can undo that addition process. What was that, Gerardo? I only have the one that I am currently drinking, and I am disinclined to give you my cooties, so no. Sorry. At some point, I will put a fridge in here and I will keep soda with me, but I am not at that stage yet. Look, mini fridge, enough to hold like a 12-pack of soda. I have not done that yet. All right, focus. Well, you got your water. You're hydrated. All right, so first example. We want to find the PFD for the problem we just did, where we added our fractions and got this. The question is, how do we undo it? We know what the answer should be because we know what that problem started as. So we're going to check that this process works with something that's familiar. So we want to find the partial fraction decomposition for 5x minus 3 over x squared minus x. So I'm going to do this in steps. Step 1. What should I do? Factor the denominator. Very good. So I know that x squared minus x, those terms both have an x in common. Take a minute. Let it percolate. That's divisible by x. That's divisible by x. I pulled the x out in front. I'm left with an x and a minus 1. Yes?
Oh, you do the denominator.
Yes. We start by figuring out the denominator because how many factors in the denominator tells me how many fractions I need. Always start with the denominator. So I'm going to rewrite the fraction with the factor denominator. So 5x minus 3 x squared minus, oops, not x squared minus x, x times x minus 1. And then I'm going to do step 2. What is step 2? Split up the fraction. Very good. How many fractions do I need? Show me on your fingers. 2. Very good, because we have 2 factors in the denominator. So fraction plus fraction, x minus 1. Are those factors linear or quadratic? Linear. One step down would be a constant. So constant in the top, constant in the top. Perfect. Step 3. Correct. So I'm going to take this whole fraction, every term, both sides, and I'm going to multiply by the factor denominator on the left. Oh no, you have to write this all out. Yes. And I will tell you why as soon as we're done with this example, because there is a reason why we're doing this. It's not just for funsies. Okay, so I'm going to put this over 1 just so we can get a mental image of what's going on. When I multiply the left side, 5x minus 3 over x minus 1, times x minus 1, what happens to the denominator? It cancels out. Perfect. On the left, I should have 5x minus 3. If I am doing this correctly, at the end of step 3, I should not have any fractions left in my expression. That's how I know I did it correctly. I'm getting rid of all the fractions. Okay. If I multiply a over x by x times x minus 1, what happens to the denominator? It cancels. Am I left with something extra? Yeah, that cancels. What happens to that? He's still there. A times x minus 1. X minus 1 didn't cancel. There's nothing down here to cancel with it. Same for the next guy. When I multiply the second fraction by x minus 1, what cancels? the x minus 1, the x is still hanging around. That's why we're doing practice today, tomorrow, when you get back from break. Practice, practice, practice. Gonna be fine.
This is the last thing we're learning.
No. This is probably the worst of the last things we're learning.
I thought you said that was the last one.
Well, I don't think this is that bad. But I got a lot of groans yesterday in fourth period, so. Could be worse. It could have been my stats probability test. You can ask Gabriel about it. Okay, so we're on to step 4. What was step 4? Simplify and solve for those constants a and b. Perfect. Solve for a and b. So first thing I should do when I simplify, I should get rid of my parentheses. What should I do? Start distribute. Very good. A goes through the parentheses. No, that's exactly right, Gerardo. Good. Ax minus a, because anything times 1 is itself, plus b. And then I am going to group the like terms together. All of the x's together, all of the constants together. I'm organizing the right side of that equation, because right now it's a hot mess. You will notice I have not touched the left, just the right. I see 2 terms that have x's in them. Ax, bx. I'm going to combine those together, which is going to give me a plus b x. That constant minus a doesn't have a buddy, so I'm just going to write it. And here's where our new math with fraction or with matrices and Kramer's rule comes in. That equation technically represents 2 equations. I have the coefficient in front of the linear term. I have the constant term. And I know if those 2 linear functions are equal, their slopes have to be equal, their intercepts have to be equal. Those 2 linear equations are equal. Equal means same slope, same intercept. So I know from that equation that 2 things are true. I know that 5 is equal to a plus b, and that negative 3 is equal to negative a. Close. Jala speaking. I'll send her on down. Bye. Julie, that was for you. You're headed on home. Gerardo, your instinct to start with the bottom equation is correct, because that only has 1 variable in it. I don't want negative a, I want a. What should I do? Divide by negative 1. It would be positive 3, yeah. So this tells me a is positive 3. And then I can use that along with the top equation to find b. So I know that 5 equals a plus b, and I know that a is 3. What is b? 2. Yeah. And all I'm going to do is go back to the top, and I'm going to replace a with 3 and b with 2. Bye, Julie. A with 3, b with 2. A with 3, b with 3. We're going to go back up to the top. Yeah? So I now know that that is 3. And this is 2. And the question is, did we get that right? So you go back to the top of your notes. Did we get what we started with today? Yes, we did. It was 3x plus 2 over x minus 1. This step list that I gave you undoes addition for fractions. The question is, why would we want to do this? Did anybody enjoy that process? No, I did because I'm a sick and demented human, but I'm assuming you guys did not. The reason we do this, there's a couple, but the most common one you're going to see in the near future is if you have to take calculus in college, you're going to learn how to integrate functions. Integrating means finding the area under a curve. Use it in physics and engineering and all kinds of fun things. Functions that look like that original unseparated rational function are difficult to integrate by hand, at least without an integral table. These two fractions that we broke it into are 1 over x. 1 over x. They have some constants thrown in there, but they're basically 1 over x. I know those are logs. So taking a big, ugly rational function and separating it into a bunch of partial fractions with smaller denominators and smaller numerators makes it easier to do math with. And as a mathematician who has been doing math for 30 years, I know from experience that I would rather do a couple lines of algebra at the start of a problem than 2 pages of calculus because I didn't simplify at the beginning. These are also used in types of transformations. I believe the Laplace transformation. If you're going into physics or engineering, you'll see it. Otherwise, you're probably safe. But this does come back in calculus. This is a useful skill to help you do other things. Yeah, and that's why we're practicing. That's why this is called pre-calculus, all those tools you need to do calc. All right, so questions before we get started with another example. Yes? I can scroll down to the bottom. I will scroll down to the bottom. Yes. Okay, so what I was doing down here is I recognized that both of these matched an mx plus b pattern. And I know that if 2 linear equations are equal, their slopes have to be the same and their intercepts have to be the same. And so I was matching slope with slope, that's the blue, and intercept with intercept, that's the red. And then building equations off it. No, that was a good question. We're going to do that as the last part of our solution process every time. I'm going to group them by like term, and then I'm going to match coefficients on the left and right. Okay, let's try another one. Nice, clean slate. Oh, I have to remember what I came up with as an example. So we want to find the partial fraction decomposition for 5x plus 16 over x squared plus 10x plus 24. Okay. Alan, first step, what do I do? You got your step list on your paper. What's the first step? Very good. Factor the denominator. First thing, factor the denominator. That is a quadratic with a leading coefficient of 1. So I'm going to play the x game in my head. I am looking for two numbers that multiply to 24 and add to 10. Very good, Gerardo. 6 and 10. Not 6 and 10, 6 and 4. You said it right. I just didn't. You did say 6 and 4. And then my brain immediately went 6 and 10 because I'm having a brain dead day. Perfect. Perfect. So I know I rewrite the fraction with that denominator. So now my fraction looks like 5x plus 16 over x plus 6. Children, stop fighting. X plus 4. Focus, children, focus. Put your phone away. Okay, class. As a class, on your fingers, how many fractions do I need? 2. Cecilia, can you tell me why I need 2 fractions? There's 2 factors. Very good. No, that's exactly right. Perfect. I need as many fractions as I have factors in the bottom. 2 factors, 2 fractions. Very good. Aubrey, what goes in the top of those fractions? A and B. Very good. They're linear, so I want constants in the top. Perfect. Okay, what do I do next? Multiply by the original factored denominator. Very good. And I know I did it correctly if all my fractions disappear. So we're going to multiply x plus 6, x plus 4, x plus 6, x plus 4 cancel. The left, you're always going to be left with just the numerator. On the right, the x plus 6 fraction will cancel and leave me with an x plus 4 on top. The x plus 4 fraction, the x plus 4s will cancel and leave me with an x plus 6 on top. Step 3 rather, is done. Yay. We split our fraction up. We multiplied. There's no more fractions. Jackie, what do I do next? Step 4. Simplify. Do you have a suggestion for how I can simplify on the right? We're stuck. Marissa, can you help her out? How do I simplify on the right? Distribute. Get rid of those parentheses. Yeah. So 5x plus 16 equals ax plus 4a plus bx plus 6b. You're excused. Gerardo, suggestions on what I can do next over here? We're one line above that. We're one line above that. How do we figure out how to match constants? Combine like terms. Yeah, I got to group them together before I can match them. So you're one step ahead. That's okay. We'll follow Gerardo's suggestion after Marissa's. So like term, like term, like term. Come on. Nope, that's not the color I wanted. Like term, like term. You were. So 5x plus 16 is a plus b x plus 4a plus 6b. So a constant times x plus a constant equals a constant times x plus a constant. Meaning I've got slope-intercept form on the left and the right. The slopes have to match. The intercepts have to match. So slope with slope, y-intercept with y-intercept. And I think that's where Gerardo was headed. So 5 equals a plus b, and 16 equals 4a plus 6b. Bless you. And this one I can't solve by substitution because both equations have both variables in them. My suggestion is Kramer's rule or doing an augmented matrix on your calculator. Do we have a preference? Kramer's rule, perfect. So notice the a and the b are now our x and a y. So the answers are on the left instead of the right. So we'll start with D. What are the coefficients on a and b in the first equation? A is the variable in this case. What's in front of the a? 1. Yeah, I have 1a and 1b. In the second equation, coefficients on a and b, 4 and 6. Perfect. I'm going to do that determinant right now. I get 1 times 6 minus 4 times 1, which is 2. Assuming I did that correctly. And I'm going to do the same thing for dx and dy. For dx, I'm replacing the x column, so the y stays the same. For dy, I'm replacing the y column. The x stays the same. In those missing columns, what do I write in their place? 5 and 16. Very good. The answers. And then we start the process over again. We find the determinant. So 5 times 6 minus 16 times 1 is 30 minus 16, which is 14. I don't see anyone arguing. I'm going to assume I did that correctly. And the next one is 1 times 16 minus 4 times 5, which is 16 minus 20, which is negative 4. I see some nodding. Yay! And now I have a and b instead of x and y, but the process is the same. A was taking the place of x, so dx over d. B was taking the place of y, dy over d. So dx is 14, d is 2, a is 7, assuming I did that correctly. I don't see any argument. Yay. All right, and then for d, dy is negative 4 divided by 2. B is negative 2. I see some nodding. Yes. Perfect. I just got to go back to the top and replace A and B. So up at the top, we now know A is 7. B is negative 2. So the partial fraction decomposition of our original fraction is 7 over x plus 6 plus negative 2 over x plus 4. It is. It is. Well, I've got more. I got a whole box of it up front. We got some time. We got some time. I'm going to give you about 5 minutes to check your phone, stretch your legs, shake it out, and then we're going to do another example or two before the bell rings. Yeah? Give about a 5-minute break. Let's see. I've got bathroom passes coming out the wazoo. Yeah, you might actually focus that way. It's amazing. All right. Another example. Same step list. Same step list. I believe this is example 3. All right, we want to find the partial fraction decomposition for negative x squared plus 2x plus 4 divided by x cubed minus 4x squared plus 4x. Sorry. We'll start with Megan. Megan, what's the first step in finding a PFD? Step 1. Perfect. Factor the denominator. Do you have any suggestions? Do any of those terms have something in common? They don't have a 4. They do all have an x, though. Yeah, let's pull the x out. So we'll pull an x out. That's going to leave me with an x squared, a minus 4x, and a plus 4. And then we're going to look at the thing in parentheses, the quadratic, x squared minus 4x plus 4. And the question is, can that be factored? So we're going to play the x game. What two numbers multiply to positive 4 and add to negative 4? Negative 2, yeah. So x minus 2, x minus 2. So I'm going to rewrite this fraction. We have minus x squared plus 2x plus 4 over x times x minus 2 squared. And I need a show of hands. Show me on your fingers. How many fractions am I going to need for this PFD? I see a lot of 2s. How many total factors are down there? 3. Yeah. I can see it right here where it's fully factored. There's 3 because there's 2x minus 2. So I need 3 fractions. So I have an x all by itself, a sad, lonely x. The question is, what goes in the other 2 fractions? X minus 2, and it's a repeat. Very good. Same thing with squared. Perfect. Yes, I heard you, Marissa. I want to make sure somebody else other than you is paying attention. Good. And then the question is, what goes in the numerator? Are those linear or quadratic? Pretty sure that's linear, right? X minus 2 is linear, x is linear, so this is just going to be A, B, C. Happy face. Happy face. Oh, step 2, Brandy, what do we do next? Don't shake your head, no. Step 2, step 2. Good, what am I going to multiply it by? The denominator, good, the factor denominator. Perfect. And I know what's going to happen on the left. The denominator should cancel entirely. So on the left, I'm just left with the numerator. On the right, anything that's not in the denominator will be left over. It won't cancel. So for the a, the x is going to cancel. The x minus 2 squared is not. A dropped out, the rest was left over. Second fraction, I'm going to have a b. And I heard I'm going to have an x, I agree. And an x minus 2, because only one of them gets canceled. Good. Plus, and then the last term, I know I'm going to have a c in the numerator. And then what's left that didn't cancel? The x. And ours on fire today. Very good. Perfect. No more fractions. Yay, I'm a happy math person. Step 3. Melanie, what's step 3? I think we just did step 3. What's step 4? Simplify. Very good. And I heard somebody use the D word. We should distribute. We are going to have one teeny issue with distributing here, and that I need to FOIL this out before I distribute the A through. So off to the side, we're going to multiply x minus 2 times x minus 2. And I know most of you said you preferred the box method. So x times x is x squared, yeah? Negative 2x, negative 2x, positive 4. Yeah? We already have that up there, but it's a good review of FOILing and box method. So I'm multiplying a by x squared minus 4x plus 4. That's what's getting distributed through. So minus x squared plus 2x plus 4 equals that quadratic times a. So ax squared minus 4ax plus 4a. For the second, I'm going to distribute bx through the parentheses. So bx times x is bx squared. Bx times negative 2 is negative 2bx. And then just plus cx. Happy face. Happy face. It did get longer because we expanded the binomials. Yeah, it did get a lot longer. It will get shorter again in a minute, but right now it got longer. We are. We're expanding in order to group like terms together. Yes, so we distributed, and now we're grouping like terms. And we're always going to do those two steps in order. Distribute, group like terms. Distribute, group like terms. So let's identify our like terms. I see x squared. I agree. I see two of those. I see an x. I see an x. I see an x. And then I see one sad, lonely constant in the middle. All right, so minus x squared plus 2x plus 4 equals. The x squareds, I have an a plus a b. For the x's, I'm looking at the coefficients in front of the x's. Going from left to right, I see a minus 4ax. I see a minus 2bx and a plus cx. There is one term I have not slapped in there yet. Which term did I miss? 4a. Very good, our constant. This is quadratic instead of linear. Our last two examples have been linear. The process is the same. If the two quadratics are equal, their coefficients also have to be equal. So -1 should match a plus b, because those are both the x squared coefficients. +2 should equal -4a minus 2b plus c, because those are both the x coefficients. +4 should be equal to 4a, because those are the only constants on either side. And now we're in familiar territory. I'm going to set up three equations. I'm going to use my knowledge of matrices and determinants to solve the equations, and then I'm done. So, question is, what do our equations look like? Dayanara, can you give me one of the equations I'm going to write? What's the red equation going to look like? A plus B. Gold star. Very good. Very good. Jordan, what's the blue equation going to look like? Where's the blue on the other side? That sounded like a combo of voices at that table, but I'll take it. Very good. Cecilia, what's my green equation going to look like? Yeah, perfect. Match the coefficients. Match the coefficients. My instinct, based on having done this a while, is I see one equation that has one letter, one equation that has two, one that has three. So I'm not going to use matrices. I'm going to use substitution. I'm going to start with A, and then B, and then C. So we'll start with the bottom. If 4 is equal to 4a, what do I know a is equal to? 1. Very good. Pretty straightforward. Then I'm going to pull the next equation. So my next equation says -1 equals a plus b, and I now know a is 1. So -1 equals 1 plus b. How do I solve for b? Subtract 1. I would subtract 1 to undo the plus 1, which means -2. Ethan, you were a little ahead of yourself with the answer, but not the house you get it. Good. Last step. I'm going to grab the equation I haven't touched yet, and I'm going to substitute in the two values that I know. A is 1, B is -2. So 2 equals -4 times 1 minus 2 times -2 plus C. On the right, -4 times 1 is -4. -2 times -2 is +4. I am pretty sure that those two things cancel and we just get C. A is 1, B is -2, C is 2. Perfect. We go back up to our original equation where we split it up and we replace. There's no quitting in math class.
It's tricky. I think it's gonna get easier.
Yes. All of my students last year, and about twice as many of them took it last year than this year, all said trig was easier than pre-cal.
So it's really just the hard lap, and then the second lap.
The second lap is easier, yeah. Which is perfect because second lap you guys usually all have senioritis and nobody's paying attention anymore.
Yeah.
So this time. All right. We've got about 20 minutes left. What I'd like you to do is give you some time to work on your delta math. Yes? And then we will practice more with this tomorrow. We'll do another example. You'll have some time to practice in your small groups. Sound good? Okay. I expect to see everyone working on their delta math, not playing on their phone, not doom scrolling on Insta. We're doing our math. Yes?